Hello and welcome everyone to today's episode. Today we are going to be covering the following topics. All the timestamps are in the description below. And I hope you enjoy today's episode. So let's get started on these topics. So let's explain what this intercept value actually means. So within our linear regression, we can get this intercept value from the model. So the way that you get this value is by using the model intercept. So here we're accessing this property of the model, and this model has been created up here. So you can see where we create the model is we create an instance of the linear regression class, and then we train our model by using the fit method. And once we've done that, basically your model then automatically has these variables populated within it. So these properties could be accessed. So intercept in this instance is 79. So why is this 79 and what does it actually mean? It means for our houses that we predicted the house price for. So for example, this is the size of the houses in our data set that we had, and these are the prices. So the first one, 650, is the size, and the price of the house is 200. So these are in square feet. So the bigger the house, the higher the price. So these are the past prices. So what happens is when the model is built, it is basically predicting this red line. So the blue points are your training data set, as I showed you above. So those are sizes and prices. And we kept two values in green to test our model, but they are actually from the data that we have here. So again, randomly selected as per my previous explanations. So what we do is we are predicting basically the formula for this line. And if a house is where, we have to predict based on the size of the house for the prices that we could get. So you could end up with a house that is 0. So when it's 0, then that's what the intercept value actually means. So here we have an intercept value of 79. So if we use the model to predict a house price, so we have 1000 here square feet, but what if we said don't predict it for a house that is 1000 square feet, predict it for a house that is 0 square feet. So if we do that and run this model, what we'll see is the predicted house price is 79. Why do we get the 79? But if you look at the intercept, that's also 79. And then this has been rounded. But if you look at that, 68, that rounded one up. Now we're taking to 69. So 79.69. So that's why the intercept value is used, because that is your base figure. So if you have a house that is, for example, 1, then, or in this instance, 0, it always has to start somewhere. So the minimum price is $79,000, and that's your starter price there. So now answering your question of the intercept value here, 79, does it actually make sense when the house size is 0? So this is a bit of a mathematical anomaly that you just need to get comfortable with, which is this is a value that is basically drawn on the line over here, and it just intercepts the y-axis. That's all it is. So when we say predict a house price with a size of 0 and we get the 79,000 figure, we shouldn't take that just because the model says that this is the figure. We shouldn't accept it as the truth, because we know that a house with no plot size, that is basically 0 size, how can that be worth 79? That's just the things of a virtual reality and of dreams. You cannot have a house that is 0 in size and still worth 79,000. Otherwise, people will think you're crazy for even thinking. So you just need to be comfortable with the fact that due to the nature of how this mathematical formula is worked out for a straight line, you get this artifact value, which is the intercept value, which makes sense in certain situations. But even if you, for example, were to say, okay, what about house which is 1 square feet? That is clearly a very small house. If we do that, and what you will see is 1 is keyed here. If I run this, and now you can see that it's saying the house is worth $79,000. And this again doesn't make sense, because 1 square feet house cannot be worth $79,000. So this intercept value, think of it just as an artifact as a result of this formula generation that lets you do predictions using a model, but you do need to be be very conscious to not put in silly values like this and then say, oh, that's what the model is predicting, so it was right. So again, in the context of things, remember this was your data over here. So we had the size and the prices there. You need to do it in that context. Actually, this is, an average house size. That's where it starts from. This is where it ends. But you cannot have, a house that is 1 square feet, 2 square feet, 3 square feet. So even if you were to change this to over here, if we change this to 4 square feet and run this again, it just doesn't make sense that it's worth $80,000. So let's have a look at the coefficient. And what does coefficient actually mean for linear regression? So remember what our purpose is. We are trying to predict based on the past house prices, based on the size of the house. So if the size of the house is 650, then it was sold for 200. So these are the actual past prices. And what we're trying to do is we just trying to predict this formula over here, as you can see. So we are just trying to predict the formula for this line. So the formula for this line is actually something we did in our math classes at school, which is we use M value multiplied by the size plus B. So what are these? So M is actually your coefficient. So what does that mean is every time the house price goes up by 1, you multiply the size of the house. So if we have a size of 1, you multiply it by this value. And if you have a size of 2, you multiply by this value. So you get that bit over here. So that M there is basically your coefficient for the M value. And of course, size is based on what size of the house you're trying to predict. And this B value is the intercept. So over here, we have an intercept of 79. So let's play this formula out. So if we have, for example, now this is not true, but if we have a house which is of size 0 and we try and predict its price, what you'll see is it matches the intercept value. So 79.69K and 79.689, but if you round that off, that makes it 69. So 79.69, 79.69. But if we increase the price, so if we increase the size of the house over here and change it to 1 and then run this, what you'll see is the price has actually gone up by this value. So the reason this has happened is it has taken the intercept, which is value over here, then it has added to it M times size. So what was M times size? So we said 1. So it has basically added on 1 coefficient value of 0.211. So if we get our calculator here and manually work this out. So we've got the coefficient here. So we'll take that value. So that's the value, that's the coefficient value, and we'll multiply it by 1. So that just basically gives you the value itself. Plus we will add in the intercept value over here. So now we've added the intercept value over here to match that. So we got the total value. And now when we press the equal sign, notice that the price we get is 79.90. And that's why you get this predicted from the model when you have a house size of 1. So just to continue explaining coefficients and how they work, remember the coefficient is this part of the formula. So essentially what you're doing is you're multiplying the size by the coefficient. So M over here multiplied by the size of the house, and that coefficient value is over here. And the way you get this from your model is very simple. So once you create your model, so remember, for us, it was very simple. We just had this sample data that we wanted to feed into a model, and we created a variable called model, created an instance of this class, and then applied the fit function. And this would take in our data that we had, the X values and the Y values. And once we've taken those, the model is ready. And from the model, what you can do is you can then extract the coefficient by using model.coef underscore, and that would give you the coefficient value. Now, this value, you may have noticed I've labeled it twice. It's also known as feature importance. But the way you get this, remember, I'm just using the code here. So I'm just coding a coefficient over here at the label, and then I'm printing model.coef. I'm doing the same thing. It's just called feature importance. And again, I'm just printing that. So it's the same value. So as you can see from the output, feature importance, 0.211. And here we also have 0.211. So it's the same value, just different way way of referring to it. Some people may call it feature importance. And the reason it's called feature importance is essentially every time this feature size changes, what should this value, the sum of this value should change by. So essentially, if it's 1, then you'll just get 1 multiplied by this. If it's 2, you'll get 2 multiplied by this. The same exact number. So this number coefficient doesn't change at all for the model. It will stay the same based on when you created the model. The only thing that changes is the size. So as the size of the house increases, so if we have a look at the graph over here, each time the size goes up by 1. So when it goes up here and here, that value will get multiplied and it keeps on increasing. That's why this is called linear regression, because it's increasing in a linear fashion. So that's basically the basic formula, but you use this code to retrieve the coefficient value from your model. So let's have a look at this mean absolute error that we get. So by mean absolute error, it's just on the test data that we used. So we can use this to evaluate how good our model is. So what we've done is, based on the data we had a house with the size of 1,500, and that's worth $400,000. So a size of 1,500 and its past price, actual price was 400. So when we look at the data and we ask the model now to predict it, let's see what price it comes back with. So the price it comes back with is 396. 396 is the price it is predicting, but we know we actually have the actual value, which is 400. So going back to the mean absolute error, this is, remember, done on the test data, but it is saying on average, if you were to predict a house price based on size of a house that you give, it doesn't have to be already existing in the data, but it can be anything, 1,500, 1,600, 1,700, whatever that you want. It predicts that there's a chance that it will be off by $4,000. So if we have a look at our example, the predicted price is 396.19. So $396,000.19. So this price that it's predicted versus the actual value, now we know the actual value because we fed the value with 1,500 is $400,000, and that's off by 4. So based on that, remember our R2 score for accuracy was pretty good as well, 0.999. So 3 nines there. So it's no surprise at all that the mean absolute error is saying that the value that you predicted could be 4,000 lower than this value. So it could be, the actual value could be 392, or it could be 4,000 higher, or it could be 400,000 and so on. So in this case, it's actually proven to be very good because the figures here are very close to the actual data we had. But that is not always the case. As we'll discuss next, sometimes the value and the difference you get here is much greater. So the mean absolute error, although it will say 4,000, but what you may end up with when you compare it against the actual price, it'll be a greater difference between it. But for now, in this instance, it's worked out very well, and it's actually pretty good based on what the model produced. But there's more in understanding this, so I'll catch you next time. What are the weaknesses with this mean absolute error? So as you can see, we previously matched this. It was pretty close. We predicted a house price over here of 396,000. The actual one in our data that we did have was 400,000. So the 396 versus 400, that's 4,000 difference. So in this instance, the mean absolute error was pretty close to our figures, but that's not always the case, because what you can see from this graph is sometimes the model will over predict. So some values are over. So here, this one is the actual value, but you can see it's over here. Here again, the actual value is under the line, but the model has predicted a higher price, but sometimes it is actually lower. So here, this value is actually actual price is higher, but the line is under it. So this means that the line has predicted a lower value versus the actual. So the mean absolute error, what it's doing is basically checking the average difference between the point and the line, and then what it does is it sums them up and then shows you what the difference is. Now, the only thing to watch out for is we've done it on the test set. Now, we we only have two test data points here, which is the 2 points in green. So one is up here and the other one is down here. So it's just based on that. Now, in our case, we've been quite lucky. It's actually been pretty accurate. But if we try and predict the house price for a different house, so rather than 1,500, let's do it for 1,000. And do we have 1,000 in our values? So let's have a look. So we do have 1,000 actual value of the size of the house, and the predicted, well, the actual price has been 300. So let's see, what does our model predict? So based on the line, what do you think you will predict? So it'll go somewhere around here, and then wherever it intercepts this line, it's going to try and predict the price. So we can see roughly, yeah, pretty accurate, but let's see what actually happens. So this is the actual value, but you can see it's already on top of the line, but the line is lower. So the line is clearly going to predict a lower price. So let's see if that's actually true by running our code. So we'll just click this play button, and what do you know? It has predicted a price of 290. So this 290 is clearly, the original price was 300,000 is out by 10k. So this is where I was trying to show you that you will get these differences in mean absolute error values versus the actual results that you may get over here versus here. So how do we actually calculate mean absolute error? So we've seen that we've got a value of 4.35, and since these are house prices, this is 4,035. So that's what the difference is between actual and predicted. Now we worked it out on the test data. This is important to understand. When we created our model, we split our actual data here into training and testing. The testing part was split out so we can evaluate, basically keep some values hidden from the model, so then we can use them to test our model. So basically, show if you were to get a student to study, maybe you can give them all the questions and answer the syllabus of the subject, but keep 2 questions or 4 questions, whatever that you want, or 20% of the content hidden in terms of the questions. You can access the past questions, past question papers and answers. So rather than give them access to all the past papers and answers, so they basically remember the answers, keep that data hidden from them so that you can let them practice on the question and answer that you do give them access to help them understand how the question and answers work, but keep some of them to yourself so that you can actually then explain to them how you can actually then test them, how good they are at answering questions. So same here. So we kept some data separately, and that meant keeping just 20% 2 values because our data set is very small. So this is absolutely fine. 2 values is 20% of the total data. And what we did was, in order to calculate the mean absolute error, we imported in this function from sklearn metrics. And then in order to use that, what we did was we shortened it as MAE. So this is the alias for it. And then we gave it the Y test and Y test predicted. So there were 2 values that we had. So over here, we had the 2 values. So that's your Y values, and the predicted values, as you can see here, we pass it the X values for the test, and we ask it to predict the Y values. So we have the actuals being compared against the predicted, and that's what gives you mean absolute error. So why do we actually need mean absolute error, and why do we need it on test data? Couldn't we have used this on the actual data? Let's try and understand this with a graph. So the red line, as you can see here, is the predicted line by the model. The blue points, as you can see here, and so on here, are all the actual values in our data that we use to train our model on. But we kept 20% of the values. Now, since our data set is very small, that meant we only had 2 values in green over here that we are using for testing. So why do we only use these 2 values over here? And how does that relate to the mean absolute error? So this is a bit of a blind date test. Essentially, what we're doing is we're keeping the 2 values that we have here for testing. Is because we don't want the model to learn from it. So it's like keeping 2 questions hidden from your child, so you can then later on test them to see if they can work out the correct answer without giving them the answer. So with the training data set, essentially what you're doing is you're giving the model the answers and the questions, so the model is able to learn. But if you kept some data hidden from it, it has no way of knowing it. So then you can use that to test and check, did you calculate this formula for this line correctly? So did you work out the correct algorithm for this calculation? And so all this does is it checks based on the test values that we kept hidden, it then uses those test values to predict. So what we go is we kept the two values, y test values. So you can see here the values that we kept hidden. So x and y. So this is the x-axis and that's the y-axis. So y is what we are trying to predict. So what we did was we asked it to work out the y values from the test data points. So we had two of them. So it's going to go ahead and use those two x values and then give us an output by using this predict function, the values that it comes across. Then what we can do is for the mean absolute error is we know the actual values from y test. So we know them. We can just use this, the predicted values that we got here. So we got the predicted values over here from this function and we just compare the actual versus the predicted. And once we have that, that's your basically mean absolute value. And all it's doing is checking basically if the green value here, that's the actual, is that under or over, and what is it under or over by? And same one here for this point, is it under or over? And it sums them up and what's the difference between the line and these points? That's what basically mean absolute error is. How does it deviate from the actual? And that's the calculation for mean absolute error. And why we use it? Because it gives us a good indication of how accurate our model is. So the difference between root mean squared error and mean absolute error isn't that great. So you can see one is higher than the other. This is because what a root mean squared error tries to do is it tries to make the differences blow out a bit better, especially the large ones. So here, this one is higher than that. It's higher than that. It's because it is penalizing the larger differences. So if we have a look at our graph over here, in this value here, we have the actual value that is under the line. So what this does is when it's under the line, let's say it's under the line by 2 points, what this will do is it will make it into 4 points. It will penalize it. While the mean absolute error doesn't penalize it as in the greater effect as the root mean squared error. So it's a bit more linear treatment of the errors. While the root mean squared error is actually quadratic, which means that it's highly sensitive to increases errors that we get. It makes them bigger. So it gives the higher weight to large errors better. So this is generally better when large errors matter more. So another way you can think of this is more of a medium error. This is more of a mean error. So depending on the situation, you may want to pick this, but both should be considered. So you can think of this as median error and this as mean error. And with median and mean, they have different purposes. Same with this one, mean absolute error and root mean squared. They have their own purpose depending on your model and what you're trying to do. But both, in this instance, I would say both should be considered. So you get a feel for how far your models are in terms of predicting the data that you feed into it. So both are good and both should be encouraged to be used so you can understand what's going on with your model. So one thing to remember is this does make the errors seem a bit more obvious, while this one sort of hides them slightly. Not greatly, but slightly. So this just treats the errors equally, while this makes the errors stand out a bit more from the crowd.